How we power our future is one of the great challenges facing the United States today. When I talk about powering the future, I'm really referring to three things. Having sufficient fuel for our vehicles so that we can move around. Having sufficient electricity on demand for whatever use that we want. And doing the first two with the minimal use of resources and minimal effect on resources. And by resources, I'm referring to the environment, land use, money. All of those play into this. These are factors that arise often in the policy debates. Not only do we have enough oil or do we have enough electricity, but should we have enough electricity? How are we coming by it? You're asking this question not because we don't have enough fuel today or enough electricity today, but we have the feeling that we're slipping. A couple of years ago, a worker went into a substation in southern Florida and made the wrong switch turn, and all of Florida went dark for a while. Why wasn't there enough redundancy in the system to keep Florida up? Same thing happened, a very similar sort of thing happened last year in Arizona, and a large part of Southern California with millions of people went dark. We import a little over 45% of the oil that we use every day from politically unstable countries, as well as others, at increasingly volatile prices and that seem to be trending upward. The institutions that we have don't seem to be responding quickly enough. But even with this sense of slipping, that creates the recognition of the need for innovation and perhaps a greater receptivity towards innovation, which is how you're going to answer the question, how we power our future. I'm going to take us through a very high-level description from the beginning of this country of the relationship of Americans to their sources and uses of energy. And then I intend to point out where the opportunities for innovation are, where you have the chance of the quickest impact, even if it's not the greatest impact, and where the long-term, where the impact will be longer term in coming, but perhaps greater in scope. As we go through this, I'd like you to keep three basic factors in mind that you as students in engineering and business schools have. One is scale of production, economies of scale. How much does it cost per unit of output as far as the final price? The efficiency of the conversion of one form of fuel to another, oil to gasoline, a fuel, whether it be coal or oil or uranium or wind or the sunlight, to a form of electricity, and energy density. These all play into the question of what the appropriate innovation is going to be. So at the beginning of our country in the late 18th century, if somebody wanted to set up a business that needed energy, they went to the source of to a source of energy. The source of energy didn't come to them. Here we have a picturesque New England mill for grinding grains or processing wood. It was sited next to a falling water that created the mechanical power to grind the grain or to process the wood. Using falling water was not a thought that arrived in the late 18th century. It had been used for time immemorial. And from an innovation context, it's a use that has been developed through the course of our country. The entire western United States, the development of cities and industrial centers depended in large part on the federal government building dams on the major rivers and generating electricity. And even part of the industrial base that enabled us to win World War II came from the electricity generated from the very large dams on the Columbia River in the Pacific Northwest that also led to the population and development of the Pacific Northwest. And even today going forward, innovations are being made to squeeze as much energy with as little impact out of falling water for the generation of electricity as possible. And around that time and going forward, if an American wanted to travel someplace beyond the scope of his or her legs, they got a horse. And if you wanted to go off with your friends or haul freight, you put a few horses together and created horsepower, like the stagecoach. Now the horse is, and other animals were very efficient sources of energy. You fed them well, they moved you with mechanical power. There was perhaps an issue of a minor amount of emissions, and the low person on the totem pole wound up having to deal with the emissions from the horse. But if you treated the horse well, it recharged overnight. If you look at the horse again, though, in with different eyes, and in the context of today's sources of renewable power, a horse or other animal can be thought of as a biodigester. It takes in some form of organic food that has an energy value, it processes it, and it emits something that has an energy value. And if you substitute a turkey for a horse and think about the emissions, I can take you to an 50 megawatt electric generator in the southwest town of Benson, Minnesota that runs on turkey poop. And the concern is not the quality of the turkey poop as a fuel, it's having enough to keep the plant running. So again, innovation can be found in very unlikely places. So let's fast forward over time. We had the development of the steamboat by Robert Fulton, the development of the train, but that really is an advance in kind from the horse and mechanical power. Come to the end of the 19th century, and Thomas Edison developed the electric light bulb. The significance of the bulb in the first instance is that you had a clean source of light that didn't require burning fuel in your house, kerosene or whatever, stinking the place up, running the fire risk, and so on. The second implication of the electric light bulb is that it removed the use of energy from the source of energy. Thomas Edison teamed up with J.P. Morgan, who was one of the great financiers of the late 19th century and early 20th century, helped build a lot of the industrial base. And they built the first central generating station in the United States, the Pearl Street Station in downtown, in the part of Lower Manhattan, solely for the purpose of providing electric current for lighting. This development of developing electric generation for lighting continues on in the names of companies today, even around here. Florida Power and Light Company, United Illuminating Company in Connecticut. And what they did was to come up with not only a generator, but some distribution over wires, over city streets to this small area of Lower Manhattan. And what developed from there was an explosion, both in the imagination of the types of uses that could be made of electricity, and with that, the need for electricity, as well as the size and the scope of the generating sources needed to feed that demand. So that over the ensuing 100 years, the 1.1 megawatt, 1,100 kilowatt, very rudimentary generator that Thomas Edison and J.P. Morgan put together on Lower Manhattan evolved to thousands of plants that look roughly like this. This is a coal-fired generating station. It's 500, 600, 700 megawatts. It cost hundreds of millions of dollars. If replicated today, it might be closer to $1 billion. There are thousands of these scattered throughout the United States, connected to end users through a tightly integrated transmission system that operates in the east and the west, as well as the state of Texas. Part of what was lost in the increase in the scale of production, as well as the scale of use, though, was part of the efficiency in going from one form of energy to another. Some of you'll see the emissions, the plume of emissions from this plant and think that's pollution. Another way of looking at it, though, is that is the efficiency loss. Approximately 60% of the energy value of the coal or uranium or whatever that goes into firing a boiler to turn a generator goes up the stack. 60% of it goes up the stack as lost heat, as lost energy. The remaining 40% goes into creating electricity. By the time it reaches the end user, the actual efficiency is way below below 10%. The other thing that this size unit and these thousands of units, as well as the transmission lines, represent is invested capital. Invested capital has brought with it the development of regulation on state and federal levels for three purposes. One was to ensure that capital will be available to build plants like this and ensure that there will be an adequate supply of electricity to users in the United States, both for their own comfort and for industrial development. The second reason for regulation was to make sure that the price at which electricity was sold was reasonable, so that consumers wouldn't be gouged, because the electric utility industry is a natural monopoly, or at least it was until recently. And the third was to bring some balance in the development of plants like this to the use of resources, to ensuring that the footprints were reasonable, and that to the extent there was an effect on the environment, it was a necessary effect. Regulatory commissions and courts don't necessarily get that right all the time, but that is one of the purposes of regulation. And one of the institutional issues that has to be dealt with when you want to do things differently, when you want to introduce a different way of generating, of using, and whatnot. So today's power grid looks something like this. The generation, whether it's this size, or it's solar, or it's wind, is connected to a high voltage transmission grid, and then to lower voltage distribution, and then into your house. From an innovation scale, where you can make a difference is in use, and it's easier to design different ways of using electricity or different ways of avoiding the use of electricity. And a similar concept applies, I think, to vehicles. You can, with fewer institutional barriers other than research, development, marketing, getting public acceptance. Then at this end, this end is heavily regulated. There's a lot of invested capital, which brings with it necessarily a lot of institutional interest. Whoops. A lot of institutional interest. It takes a long time to develop a plant. Even wind developers that I work with, it takes, for large-scale development, it takes 7 years to develop and get the plants constructed. For nuclear plants and coal-fired plants, it takes even longer. So to displace these, or to replace these with something more efficient and with a similar amount of capacity, with a similar amount of supply, takes a longer time. But if you replace them, you will have a broader impact than the individual impact, the sum of the impacts at the user end. So what's been happening at the what I call the quicker and perhaps smaller local impact end? A group got together and designed a new home thermostat. This is a programmable thermostat, unlike the ones that many of you, and certainly I was used to. I don't need an engineering degree to figure out which buttons to push. You walk up to it, you change it to the heat or cooling level that you like, you walk away. Your mother may come down, or your son or daughter may come up and change it again. And over the course of about 2 or 3 weeks, this thermostat will figure out by itself what's the appropriate heat at the time of day in the season, and along with conditions outside. It has sensors, it has computer chips, it's programmable by phone. It was brought to you by the same people who developed the iPod. It will help users control the amount of energy that they use. Buildings in the United States use 40% of the energy used in the United States, and one of the best ways to reduce that need is by greater efficiency. The iconic development of recent days has been the complete makeover of the Empire State Building. After an extensive analysis, all the windows were replaced, all the controls, the HVAC was replaced, the tenant layout was replaced, and the net result that was sought by the building owner was a 38% reduction in energy use and a $2.5 million a year reduction in energy cost. That's the type of business proposition that will get businessmen interested. in this type of efficiency. And in large cities where the rates are high, there's a business case to be built for, to be made for those sorts of makeovers with a minimum of regulatory objection. Then we get to electric cars. You're going to hear about that later today. The purpose of going to an electric car is to reduce emissions, to be more environmentally friendly, and to be more environmentally consistent, efficient. The big challenge for electric cars, I think, as you'll hear, is the creation of batteries or some other form of locomotion that meets the efficiency test, meets the scale test, both in terms of scalability of production as well as scalability of cost, and the energy density. The energy density being probably the biggest issue to face. Right now, the Chevy Volt has a 40-mile cruising range. The Nissan Leaf has a 100-mile cruising range. The Chevy Volt being a sort of a hybrid and the Nissan Leaf being an all-electric. There's another, the Coda, I believe, has a 125-mile range. That's great for commuting, assuming that you have recharging stations. But as far as general acceptance and price-worthiness, the consumer case needs to be made. And the consumer case needs to be made in order for the other institutional changes to be made, to make it worth electric utilities' while in order to provide recharging facilities, or for individual entrepreneurs to figure out how to build the infrastructure for recharging that will allow a greater scope of range for electric cars. And with that comes the needs of capital and business. Now, let's go back to the future. In New England, the businessman sought the energy source. These days, we're trying to bring the energy source to us. That's the rooftop solar. There are technical issues. The rooftop solar doesn't quite fit the energy usage of the house. During the day when the sun shines, the usage is greater. When the sun doesn't shine, there isn't any. There's a need for batteries. But what makes the infiltration of rooftop solar helpful are regulations that require utilities to buy the output at a reasonable price to help make the business case while the technology develops and the efficiency, the conversion factors increase. On a larger scale, similar issues arise with utility scale solar. The output is measured in kilowatts here. In a utility sense, you're looking for hundreds of megawatts in the appropriate place. In the large 300 megawatt concentrating solar project being built in the Mojave Desert takes hundreds of acres. It requires a lot of land. It has certain environmental impacts. There are costs of connecting to the grid. It simply has taken longer to develop. And finally, I get back to the large-scale generation. Even the generation that we have, there's a demand for greater efficiency and the reduction of pollution and making a better business case for the continued operation. The focus of policy these days is to reduce greenhouse gas emissions, carbon dioxide, and others. And you hear the terms carbon capture and sequestration, and they are different. Carbon capture is capturing the carbon dioxide from the production stream before it's emitted in the plume. Sequestration is figuring out what to do with it. A lot of the focus about sequestration is building pipelines to inject it into the ground. That's a mechanical answer to what I think is a chemical question. Our firm is working with a company that has reduced carbon dioxide to this. It's sodium bicarbonate. It's not yet ready for commercialization. It's in the developmental stage. And the purpose is not to develop sodium bicarbonate, but to develop a building material that will create a revenue stream for the utility operator and greater efficiency in the generator's operation. So because prices are going up, because the populace is unhappy with the effect of energy production on the environment, because of political uncertainty, there is a yearning for innovation as long as the innovation is easy to use or even transparent, like the thermostat or like the retrofit of the building. It is compact, it is energy dense and powerful, and it's affordable. That's your challenge. Thank you.